Now we start with diagonal canonical form part 2. In this we will study modeling of diagonal canonical form part 2. Part 2 means here degree of numerator is same as degree of denominator, that is part 2. Numerical example, and finally advantages and disadvantages of canonical form of modeling. Now part 2 diagonal canonical form, here degree of numerator is same as degree of denominator, that is proper transfer function. In last part we have seen a model, a diagonal canonical form of model where degree of denominator is greater than degree of numerator, but sometimes it may possible that in practical system degree of denominator is same as degree of numerator. So in that case how will you develop the model? So now here what we will do, we have to develop the model when the case is like this. So for that purpose we will take one system, a transfer function system, that is ys by us equal to b3 s cube b2 square plus b1s plus b naught divided by s cube plus a2 square plus a1s plus a naught. So in this transfer function b0, b1, b2, b3 are the coefficients of the numerator and a2, a1, a0 are the coefficients of the denominator. And in this case what we are assuming that the eigenvalues of the denominator are distinct, they are different, they are not repeated. The how to develop the model, and problem is that in this model here the degree of numerator and denominator are same, it is difficult to apply a partial fraction expansions, because in order to apply partial fraction expansion degree of denominator should be greater than degree of numerator. Now how to handle these issues? So here what we do, we will convert this proper transfer function into strictly proper transfer function. So what procedure we apply? What we will do, we will write this b3 s cube as b3 in bracket, we will write down s cube plus a2 square plus a1s plus a naught. So what we want, b3 s cube, so b3 s cube is there, so this additional term we added, therefore we will subtract these terms as b3 a2 square plus b3 a1s plus b3 a naught. So what will happen, if you make subtraction of this one, we will get same b3 s cube plus b2 square plus b1s plus b naught divided by s cube plus a2 square plus a1s plus a naught. So here little mathematical adjustment we have made, but finally we will find that the result of this equation, let us say this is equation number 1 and equation number 2, both are same. These terms will automatically cancel, this b3 a2 square, b3 a1s, b3 a0 with this one. Finally we will get the same b3 s cube, b2 s square, b1s b naught divided by s cube, a2 s square, a1s plus a naught. Now what we will do, we divide both equations. So after division of this, what we will get? We will get b3 plus s square b2 minus b3 into a2 plus s b1 minus b3 into a1 plus b naught minus b3 into a naught. You just see here. So, you will find that s square terms equal to this b2 minus b3 into a2, then s terms this s b1 minus b3 into a1 and plus b0 minus b3 into a naught divided by s3 a2 square plus a1s plus a naught. So, we will find that original transfer function is proper, whereas after doing some mathematical adjustment this transfer function has been converted into a strictly proper transfer function. Why we have done it? It is because we have to take inverse Laplace, and inverse Laplace it is better to we should have strictly proper transfer function. Now we follow the same process which we have followed earlier now, that is B3 plus we can write down C1 S plus lambda 1, C2 S plus lambda 2 and C3 S plus lambda 3. That means we assume that this denominator has 3 eigenvalues lambda 1, lambda 2 and lambda 3, they are distinct. So, B3 C1 S plus lambda 1, C2 S plus lambda 3, C3 S plus lambda 3. Now what we do? Now we will solve this. So after solving we will get S plus lambda 1, S plus lambda 2 and S plus lambda 3. What we will do? We will take this part only, this part and this part. So equation number 3 and we take equation number 4. So what will happen? S plus lambda 1, S plus lambda 2, S plus lambda 3. So after solving what we will get? We will get C1 S plus lambda 2, S plus lambda 3 plus C2 S plus lambda 1, S plus lambda 3 plus C3 S plus lambda 1, S plus lambda 2. So now we have got this equation and this equation, and we have taken this B3 separately. So let us say B3 plus this is, but now we are comparing this equation 3 and 4. So when we compare the equation 3 and 4, what we will get? Now we can write down as S square B2 minus B3 into A2 plus S B1 minus B3 into A1 plus B0 minus B3 into A0. So what we have done? We have taken these particular equations, this equation, and we have to compare with this. So we write down this as C1 S plus lambda 2, S plus lambda 3 plus C2 S plus lambda 1, S plus lambda 3 plus C3 S plus lambda 1, S plus lambda 2. That is this particular part, this part we have taken like this here, and this is the particular part we have taken. Now we have to, our aim is to determine the values of C1, C2 and C3. As I told last time also, there are two ways we can solve this equation and compare the coefficient of S square, S1 and S0. Second method is that we can replace the different values of S. Let us say first of all we replace S equals to lambda 2. If you replace S equals to minus lambda 2 in this equation, so what result will get? If you replace S equals to lambda 2, so this becomes 0, then this part is also becomes 0. So remaining will be the value of C2. So finally if you replace S equals to lambda 2 here, we get the value of C2 as, okay, we can get the value of C2 as C2 equals to B0 minus B3 into A0 minus lambda 2 B1 minus B3 into A1 plus lambda 2 square B2 minus B3 into A2 divided by minus lambda 2 plus lambda 1 bracket minus lambda 2 plus lambda 3. So in this way we have got SC2. Now how to get the value of C3? So let us say if you replace S equals to minus lambda 3, if you replace S equals to lambda 3 in this equation, what will happen? This C1 will be removed, then again we replace S equals to lambda 3 here, C2 will be removed, and finally here lambda 1 lambda 2, so we will get the value of C3. So therefore in this equation, so you will get C3 as B0 minus B3 into A0 minus lambda 3 B1 minus B3 into A1 plus lambda 3 B2 minus B3 into A2 divided by minus lambda 3 plus lambda 1 minus lambda 3 plus lambda 2. Now to get the value of C1, so there are two options. Already last time what I told that you can replace S equals to 0. So here we can have two options. One option is that we can replace S equals to minus lambda 1, you can get the equation in terms of C2 and C3. Other thing is that we can replace the values of S equals 0. So when you replace the value of S equals 0, you can get the C1 which is in terms of C2 and C3. So in that equation you have to replace the values of C2 and C3 and you can get the value of C1. So you can try any of the option, but now here what we do, we are replacing S equals 0. So if you are replacing S equals to 0, S equals to 0 in this equation. So if you replace S equals to 0 in this equation, so you will get C1 in terms of lambda 2 lambda 3, C2 in terms of lambda 1 lambda 3 and C3 in terms of lambda 1 and lambda 2. So finally we can write the values of C1 as C1 equals to B0 minus B3 into A0 minus C2 lambda 1 into lambda 3 minus C3 lambda 1 into lambda 2 divided by lambda 2 and lambda 3. So in this way we can have got C1, C2 and C3. So to the procedure which I have told, we will again see it systematically. So here consider third order system with proper transfer function, that is degree of denominator is same as degree of numerator. So we will take B3 s cube, B2 s square, B1 s B0, s cube, A2 s square, A1 s A0, assuming poles are distinct. The diagonal form of representation is represented in the following steps. As first stage, the transfer function of system, that is equation 1, can be expanded as B3 B2 B3 A2 s square, B1 B3 A1 s, B0 B3 A0, s plus lambda 1, s plus lambda 2, s plus lambda 3. That means here you can see this is the part, this we have shown here. Now the transfer function of 2 can be written in a partial fraction expansion. So here B3 C1 s plus lambda 1, C2 s plus lambda 2, C3 s plus lambda 3. Now comparing equation 2 and 3, so what happened? Comparing equation 2 and equation 3, so that means here earlier we have shown here, this is this equation we are comparing with this, and here this same thing, equation 2 and equation 3. So what we will get? C2, C3 and C1. C1 there are two ways to determine, as I told you that either you can replace S equals to 0 or you can replace S equals to minus lambda 1. So these particular equations we have got replacing S equals 0, and this equation we have got replacing S equals to minus lambda 1. So both the way you can do it. That means here for getting C1 you have to replace the value of C2 and C3 in these equations. As discussed earlier, the state model can be written as x1 dot equals to lambda 1 x1 into u, x2 dot equals to minus lambda 1 lambda 2 into x2, and what is the x3 dot? Lambda 3 into x3, 1 1 into u. And what is the output? Output is C1 C2 C3 x1 x2 a3. Now what is the addition thing is happened? Here we have got B3 into u. That means this B3, this y we write down in terms, that is B into u of s. So here in the output we will get, along with C1 C2 C3 we are getting B3 into u. So we will get B3 into u. And the block diagram of the system, you see that here 3 integrators, integrator 1, integrator 2 and 3. Why 3 integrators? Because you have 3 states, x1 dot, x2 dot and x3 dot, these summation blocks. Now this is input, then C1 C2 C3 which we have determined here C1 C2 C3, and here specifically it is B3 into u. So in this equation your y equals to Cx plus du, d is exist. In the part 1 we will find that d is not exist, but here d is exist. So when the d will exist, when the degree of numerator is same as degree of denominator, then this d is exist. So we have shown B3 into u. Now we study this with a numerical example, but here for the numerical example what we are doing here, we are taking a degree of denominator is greater than the degree of numerator. So for understanding purpose I have taken only second order system, that is 2s plus 5 s square plus 5s plus 6. Now s square plus 5s plus 2. So second order. So how many eigenvalues, or we can say roots? The roots are s equals to minus 2 and another at s equals to minus 3. So you will find that s square plus 5s plus 6, s plus 2, s plus 3. Now here what we want? We want diagonal canonical form. Therefore we have to use partial fraction expansion. So here 2s plus 5 s square plus 5s plus 6, it has been written as c1 s plus 2, c2 s plus 3. Now after solving, so here we have solved it, s plus 2 into s plus 3, c1 s plus 3, c2 s plus 2. So now what we do? We compare these equations. So after comparing, we have 2s plus 5 here, c1 s plus 3, c2 s plus 2. So in this case what we do? What we have done? We have replaced s equals to minus 3 in this equation. So what happened? This becomes 0. Okay. So we will get the values of c2 and finally we will get the values of c1. That means if you replace here s equals to minus 3, so this becomes 0. So what is c2? c2 is, we replace s equals to minus 3, so we will get c2 equals to 1. Then in the above equation we replace s equals to minus 2. So s equals to minus we replace, this c2 becomes equals to 0. So we will get the values of, this is c1. Not. So we get c2 and c1, and finally we have got ys by u is equals to 1 upon s plus 2, 1 upon s plus 3. The above equation can be written as 1 upon s plus 2 into u of s, 1 upon s plus 3 into u of s. Finally y of s equals to this is x1 of s and this is x2 of s, and we have written x1 of s equals to s plus 2, that is x1 equals to x1 dot equals to minus 2x1 plus u. That means here what we have done? We have used inverse Laplace transform, and because of that we have got this. Similarly, this is x2 of s, x2 of s equals to u of s divided by s plus 3. So x2 of s equal to 1 upon s plus 3 into u of s. So what we will get? S x2 x, that is x2 dot equals to minus 3x2 plus u. So from using equation this 11 and equation 12, we have got x1 dot x2 dot equals to minus 2 x1 into u, x2 dot equals to 0 minus 3 into u, and here 1 1 u, and y equals to here 1 1 x1 into 0 into u. So you will find that this system we have taken, that is strictly proper, and because of that 0 has come, that is d is 0. But in the same problem, if I have taken 5 square, 5s square plus 2s plus 5, s square plus 5s plus 6. So in that case this 5 may reappeared here, this is 5 into u, 5 into, that is case when it is only proper transfer function, and this 0 has come because of strictly proper nature, proper transfer function. So strictly transfer function you will get 0, but when proper we will get here 5u if you have taken the problem of this nature. Now we see some advantages of this approach. System matrix A is always in diagonal form, that is you will find that the diagonal elements will get the eigenvalues, and the elements are very less. Therefore for analysis purpose this type of modeling is very useful. Second point, in this approach each state equation is of first order irrespective of the order of the transfer function. These equations can be solved independently. Moreover, the decoupling of the state equation is also possible. It means that whatever may be the order of the transfer function, the state equation is always a first order, and moreover they can be solved independently, and therefore decoupling of the states is possible, and therefore we find that this type of decoupling concept has been used in checking the controllability and observability. And in state space the main important step is to design a controller. For the controller design also this type of model is very much useful. Now third, due to diagonal nature of the system matrix, it is useful in determination of state transition matrix, controllability, observability and stabilizability and detectability. So along with the controllability, observability, there are other methodologies for control design, that is stabilizability and detectability. So that can also possible using this type of modeling. Now there are some disadvantages. Similar to companion form, diagonal canonical form are not the physical variable of the system. That is, similar to companion form, diagonal canonical form are not the physical variable of the system. Therefore, they are difficult for measurement and control purpose practically. See here, whatever model we have taken, we are assuming the variables, state variables, but they are not actual variable, they are not physical variables. Therefore, this type of analysis or this type of model cannot be useful for measurement and control purpose practically, but as far as the analysis part is concerned, this type of modeling is very much useful. That means, if you are having a system, we are convert into some differential equation form, and in that case, what should be the result? What should be the predicted result? That can be possible by means of this type of canonical form of modeling. So although we find that there are some advantage, similarly for every side there is a two side advantage and disadvantage. So there are little disadvantage, but still this type of modeling is very much useful in control applications. These are some references: Chaudhary, D. Rai Chaudhary's Modern Control Engineering, Norman Nice, Ogata's, Nagrath and Gopal. So you can use these references. Thank you.